From the silent vantage point of a satellite drifting in geostationary orbit, the world looks perfectly, deceptively peaceful. There is a profound stillness in the data streams that define our modern existence. If you were to look at the real-time feeds from the Space Weather Prediction Center right now, you would see a magnetic environment that is almost eerily calm. The solar wind, that invisible stream of charged particles constantly bathing our planet, is currently flowing at a gentle 383 kilometers per second, a notable drop from the 480 kilometers per second recorded just 24 hours ago. The total magnetic field is averaging a mere 4 nanotesla, while the critical BZ component, the magnetic orientation that determines how energy couples with our atmosphere, is simply fluctuating between plus and minus 4 nanotesla. To the uninitiated, this is not just a quiet day, it is a very quiet day, with the observed KP index sitting at a low 1.33. But this stillness is a mask. Behind this facade of tranquility, a colossal event has already occurred. Deep in the heart of the solar corona, a shockwave has been unleashed, and it is currently hurtling through the vacuum of space at a staggering 1,293 kilometers per second. That is nearly 2.9 million miles per hour. Earth has not felt the impact yet, but the physics are immutable. The energy has been released, the wave is in motion, and the clock is ticking. This is the part of the story that no one is talking about. The sharpening contrast between the calm we see today and the atmospheric anomaly that is already on its way. This arrival window is expected to open late Saturday into Sunday, potentially merging with previous eruptions to create a complex, compressed magnetic cloud. To understand the magnitude of what is coming, we have to look closer at the source of this disruption. It began in a sunspot region designated as 4419, a magnetically complex scar on the Sun's surface that has recently transitioned into a state of high energy output. In a period of just over 7 hours, this single region fired 2 massive X-class solar flares, the strongest classification possible. The first, an X2.4, peaked at 1:07 Universal Time. The second, an X2.5, followed at 8:13. This was not a random outburst, but the culmination of a violent sequence. In the 28 hours leading up to these events, the same region had already launched 6 M-class flares, repeatedly ejecting plasma and energy into the inner heliosphere. Region 4419 was essentially knocking its arrows, preparing for the main blast that would send a shockwave above the 90th percentile of all observed events in the satellite era. The sun did not just erupt, it screamed. Ground-based radio telescopes picked up a specific signature known as a Type 2 radio sweep, which allowed forecasters to calculate the incredible velocity of the approaching shock. Accompanying this was a 10-centimeter radio burst that peaked at 570 solar flux units, roughly 4.5 times the normal background level. It was, in every sense of the word, loud. These flares have already caused strong R3 radio blackouts on the daylight side of our planet, affecting high-frequency communication. But the flare was only the flash. The true weight of this event lies in the coronal mass ejection, the massive wave of plasma that is following behind that flash. We are looking at a system that is no longer behaving according to the old models. Solar cycle 25 was predicted to be a mild cycle, with a peak sunspot number of around 115. Instead, it has shattered those expectations, with monthly values routinely exceeding 150 and pushing above 200. We are seeing a sun that is more active, more volatile, and more unpredictable than many experts anticipated. And as region 4419 rotates toward the sun's limb, another even larger threat, Region 4420, is rotating into a direct Earth-facing position. This is investigative meteorology. We are tracking the invisible stressors on our modern infrastructure, from the potential for CME cannibalization to the atmospheric drag on our satellites. The storm has already begun at the Sun. The silence at Earth is merely the countdown. We must look past the blue horizon, for we do not only live under the weather of Earth, we live under the weather of a star. To understand the momentum of this shockwave, we must first dissect the engine that created it. Region 4419 is not merely a cluster of dark spots on the solar photosphere. It is a profound concentration of magnetic energy, classified by the Space Weather Prediction Center as a beta-gamma delta region. This designation is the signature most strongly associated with X-class flare production in observational literature. It represents a state where opposite magnetic polarities are crowded within less than 2 degrees of a single penumbra, creating a high-tension environment where magnetic fields are twisted and sheared. This is the magnetic equivalent of winding a rubber band until it reaches its breaking point. At the time of this sequence, Region 4419 occupied an area of 220 millionths of a solar hemisphere, harboring 7 distinct sunspots that were increasingly growing and consolidating. The double X-class event was not a sudden anomaly, but the climax of a sustained surge in activity. In the 28 hours preceding the main blast, this specific region acted as a rapid-fire battery, launching 6 M-class flares in quick succession. The sequence began with an M1.6 flare at 4:31 Universal Time, followed by a pair of M1.2 events, and escalated into an M4.3 and an M1.7. The final warning shot before the peak was an M4.9 flare. More importantly, the M1.7 and M4.9 events each launched their own coronal mass ejections. While these early CMEs were aimed off-axis and were not considered major threats on their own, their existence is critical to the broader story. By launching physical plasma into the inner heliosphere repeatedly, Region 4419 was cluttering the interplanetary medium downstream. This increased the solar wind density and magnetic complexity, creating the perfect preconditions for the cannibalization defect that we are now monitoring. Then, the region transitioned into X-class territory. At 1:07 Universal Time, the sunspot fired an X2.4 solar flare. Less than 8 hours later, at 8:13 Universal Time, it struck again with an X2.5. This double tap from a single active region is significant because it suggests a system that has reached a new level of productivity. At this stage, it is vital to distinguish between the flare and the subsequent wave. A flare is a burst of light and high-energy radiation that reaches Earth at the speed of light. The coronal mass ejection, or CME, is the physical wave of plasma and magnetic field that follows behind. While the flare is the flash from the muzzle, the CME is the wave behind it. And in this case, the Sun fired twice. The flash reached us immediately. Both X-class flares produced an R3 strong radio blackout on the daylight side of Earth. An R3 event is powerful enough to disrupt high-frequency radio communications for hours, specifically affecting transpolar routes and maritime operations. But beyond the radio blackout, the Sun provided a more visceral signal of its activity. It screamed across the radio spectrum. Forecasters detected a Type 2 radio sweep, a specific signature indicating that the CME was moving fast enough to push a shockwave through the solar corona. The frequency of that sweep is what allows scientists to calculate the velocity of the eruption. This was accompanied by a Type 4 emission and a massive 10-centimeter radio burst. This burst reached 570 solar flux units, roughly 4.5 times the normal daily background level of 128. In every sense of the word, the sun was loud. These radio signals were not just noise. They were the first diagnostic layers of a storm that is now crossing the 93 million mile void between us and our star. This radio signature provided the critical data point that allowed the Space Weather Prediction Center to issue its formal alert for a shock moving at 1,293 kilometers per second. When the Space Weather Prediction Center issued its first alert for the incoming shockwave, the estimated velocity was an astonishing 1,869 kilometers per second. Half an hour later, that alert was canceled and reissued at 1,293 kilometers per second. This was not a cover-up. It was exactly what a responsible forecast office does, tightening its estimate as better telemetry streams in from the orbital coronagraphs. To put this revised number into perspective, the median speed for a coronal mass ejection sits around 400 kilometers per second. A velocity of 1,293 kilometers per second places this event firmly above the 90th percentile of all recorded data. It is blisteringly fast. Yet, in the geometry of space weather, speed matters, but direction dictates everything. Initial imagery suggested the eruption was heading northwest, veering slightly away from the Sun-Earth line. But a coronal mass ejection is not a bullet. It is a massive, expanding cloud of charged plasma. Even if the dense core misses our planet, the sheer width of the flank can still sweep over us. Forecasters have confirmed an Earth-directed component, with an arrival window opening late April 25th into April 26th. While it may only be a glancing blow, in a highly charged system, a glancing blow is all it takes to trigger a cascading systemic response. The danger of this arrival is not just what was fired today, but what is already waiting in the cold darkness ahead of it. On April 23rd, a different area of magnetic instability, Region 4420, launched an M1.2 flare that produced its own slower-moving coronal mass ejection. That earlier wave is also expected to graze Earth around April 26th. We now have a slower CME drifting ahead and a vastly faster, denser CME barreling up from behind. When these trajectories overlap, the physics become incredibly complex. The faster eruption can overtake the slower one en route to Earth, a phenomenon known as CME cannibalization. The two separate ejections merge, compressing into a single, massive magnetic cloud. The plasma density skyrockets, and the magnetic field within the cloud becomes entangled and amplified. This is exactly the physical setup that drove the infamous Gannon storm in May 2024, where a sequence of overlapping eruptions elevated a moderate forecast into an extreme G5 event. While this weekend's configuration is not currently predicted to reach Gannon-level extremes, the cannibalization factor introduces a severe upside risk. It is the reason why forecasters must keep G2 moderate storm conditions explicitly on the table. Yet, as we wait for this compressed wall of energy to arrive, the Earth's magnetic environment remains completely unbothered. The solar wind speed has dropped to a sluggish 383 kilometers per second. The total magnetic field is hovering around a weak 4 nanotesla, and the planetary KP index has plummeted to a remarkably quiet 1.33. This profound stillness is exactly what makes the incoming shockwave so significant. When a high-velocity transient slams into a quiet, undisturbed magnetic environment, the contrast is violently sharp. The ultimate severity of this storm, however, will be decided by one singular, invisible factor, the BZ component. The BZ represents the north-south orientation of the interplanetary magnetic field. If the incoming cloud has a northward orientation, it will largely deflect off Earth's magnetic shield. But if the BZ flips southward, it will magnetically couple with our planet, opening the gates for solar plasma to pour directly into our upper atmosphere. A moderate CME with a sustained southward BZ can easily overperform its forecast. Right now, the storm has begun at the star, but it has not yet reached the Earth. Forecasters can only watch the telemetry, knowing that the direction of the BZ will decide everything. Based on the current data from the Space Weather Prediction Center, the formal forecast calls for isolated G1 minor to G2 moderate geomagnetic storm conditions. The peak KP index is expected to hit 4.67 during the crucial window between 1500 and 1800 Universal Time on April 26th. To contextualize this, the G-scale runs from G1 minor all the way to G5 extreme. We are not staring down a civilization-ending extreme event today. This is not a forecast for a global collapse. However, dismissing a G1 or G2 event as insignificant is a dangerous oversight. Even minor storms carry profound technical implications, serving as stress tests for the invisible architecture that holds our modern world together. The most visible and hauntingly beautiful symptom of this arriving energy will be the aurora borealis. As solar plasma collides with gases in our upper atmosphere, it paints the night sky in vibrant shades of green and red. Under G1 conditions, this display is confined to high latitudes, but if cannibalization amplifies the impact into a G2 storm, that visibility line pushes further south. Those in the northern tier of the United States, the northern plains, the upper Midwest, and northern New England may witness the aurora, provided they have clear skies. Yet, it is vital to remember what the aurora truly represents. The exact same energy that paints the sky with ethereal beauty is simultaneously disturbing the electromagnetic foundation of our modern technology. The first systems to feel this disturbance will be those relying on the ionosphere. High-frequency radio communications on transpolar routes will experience degradation and sporadic blackouts. Down on the surface, precision global positioning systems will begin to drift. While a standard smartphone might not show a noticeable glitch, precision users, those relying on centimeter-level accuracy for automated agriculture, deep-sea operations, and geophysical exploration, will face operational hurdles. For the average person, this degradation is entirely invisible. For the systems governing our supply chains, it is a measurable disruption. As we move higher into orbit, the stakes escalate. When a geomagnetic storm hits, it heats the Earth's upper atmosphere, causing it to expand outward. This drastically increases the aerodynamic drag on low Earth orbit satellites. Orbital predictions become unstable, forcing operators to execute collision avoidance maneuvers because the thermosphere density changes faster than models track. Higher up, in geosynchronous orbit, the threat shifts to radiation. The 2 mega-electron-volt electron flux has already peaked at an elevated 3,446 particle flux units. Space weather is, essentially, infrastructure weather. Finally, this invisible stress reaches the ground, coupling directly with our power grids. Long transmission lines act like massive antennas, capturing geomagnetically induced currents generated by the storm. Under G1 and G2 conditions, grid operators will log minor voltage fluctuations. They will monitor these anomalies closely, balancing loads to prevent failures. Let me be clear, there is no evidence to suggest this event will cause widespread blackouts. We are not predicting a grid collapse. The danger here is not panic. The danger is underestimating invisible stress. We are witnessing our planetary infrastructure absorb hit after hit, in a solar cycle that is overperforming every official expectation. The systems hold for now, but our electrified existence has never been more fragile. As grid operators monitor these magnetic fluctuations, there is a natural tendency to believe that once this weekend passes, the worst will be over. Region 4419, the volatile origin of this dual X-class assault, is currently positioned near north 15 west 77 degrees, hugging the extreme western limb of the Sun. Within the next 48 to 72 hours, rotation will carry it completely out of Earth's view. While it holds a 15% probability of firing another X-class flare, its direct geo-effective window is rapidly closing. But the Sun is not winding down. What is rotating onto the Earth-facing side is significantly larger. Region 4420 has emerged at north 16 east 11 degrees. It spans a massive 250 millionths of a solar hemisphere, dwarfing 4419's area of 220 millionths. Where 4419 possessed 7 sunspots, Region 4420 commands 20. Size alone, however, is never the most alarming metric. The true threat lies in magnetic complexity. Region 4420 carries a severe beta-gamma-delta classification. In solar physics, delta spots are strongly associated with major flares because they feature opposite magnetic polarities crowded tightly together. Forecasters observe active shearing in these areas. Shearing is the magnetic equivalent of a wound-up rubber band, twisted tighter until the stored kinetic energy violently snaps. As Region 4420 approaches the central solar meridian, any eruption it produces will not be a glancing blow. It will be directly geo-effective, aimed straight down the Sun-Earth line. And as if this giant were not enough, a second front has opened. Region 4423, positioned at south 5 east 30 degrees, grew so rapidly it was only recently numbered. With a beta-delta magnetic class and an M1.9 flare already on its ledger, we are looking at a star with 3 loaded chambers. This relentless activity shatters our foundational expectations for solar cycle 25. The official forecast, published by NOAA in 2019, projected a mild cycle with a smoothed sunspot maximum of roughly 115. We passed that threshold a long time ago. Observed monthly values routinely push above 150, occasionally breaching the 200 mark. Because we are supposed to be entering the declining phase of this cycle, there is an assumption that the danger is receding. History offers a terrifying rebuttal. The catastrophic Halloween storms of October 2003, which included an X-17 class flare and multi-day G5 extreme conditions, occurred during the declining phase of solar cycle 23. The declining phase does not mean quiet. It often means the release of the most powerful, pent-up anomalies. History is not a prophecy, but it is a severe warning. Whenever anomalies of this magnitude occur, misinformation often attributes these events to terrestrial facilities like HAARP. Let us dispatch this claim with basic physics. HAARP operates with a peak transmitted power of 3.6 megawatts. A single X 2.5 solar flare releases energy on the order of 10 to the 25th joules. That is a difference of 14 orders of magnitude. No human facility can engineer a solar flare. The scale simply does not exist. We must now watch for signs that would upgrade this story. An early arrival, a sustained southward BZ, evidence of cannibalization, or an eruption from Region 4420. We are tracking a shockwave moving at 1,293 kilometers per second. This is a compounding anomaly that exposes our profound vulnerabilities. Modern civilization does not only live under the weather of Earth, it also lives under the weather of a star. As the clock ticks closer to the arrival window, the narrative shifts from the orbital observatories down to the ground, to you. We have tracked the X-class flares, calculated the 1,293 kilometers per second velocity of the shockwave, and analyzed the magnetic complexity of regions 4, 419, 4, 4, 2, 0, and 4, 4, 2, 3. But information without application is merely trivia. In investigative meteorology, our goal is not to spectate, it is to prepare. We are entering a period where the fragility of human infrastructure is a tangible variable. As we monitor the telemetry for this impending geomagnetic arrival, we must adopt a mindset of calm readiness. The systems that power our homes and guide global logistics are vulnerable to the anomalies of a star breaking its own predictive models. This is why we do not rely solely on the delayed reports of conventional networks. We build our own situational awareness. As this coronal mass ejection crosses into the inner heliosphere, I am calling on you to actively participate. This space is not just a broadcast, it is a global command center, and you are the distributed network. I want you to initiate our global roll call right now. Sound off in the comments with your exact location, your current weather, and any anomalies you observe in your local power grids or radio equipment over the next 48 hours. Whether you watch from the plains of the Midwest or across the Atlantic, your ground-level data is critical. When the BZ component flips southward, your localized reports will reveal the true story of this storm's impact. Being prepared does not mean surrendering to panic. It means stepping into a position of calm authority over your environment. Take this profoundly quiet window before the arrival to review your redundancies. Ensure critical communication devices are charged. Verify secondary power sources, whether portable solar generators or traditional backups. Relying entirely on an aging centralized electrical grid during intense space weather is a failure of foresight. Grid operators will do everything possible to balance the geomagnetically induced currents, but they are fighting an invisible tide. You must become the final line of resilience for your family and community. We must recognize that this weekend's arrival is not an isolated peak, but a precursor. With region 4420 rotating into a direct Earth-facing alignment and region 4423 expanding rapidly, the next 2 weeks demand sustained vigilance. We are witnessing a fundamental shift in solar cycle 25. The old consensus that promised a mild cycle has been invalidated by the relentless volume of eruptions we are cataloging. We are moving into an era of compounding disasters, where terrestrial extremes, like stalling atmospheric rivers, will overlap with severe space weather events. When a local grid is already strained by severe earthly weather, a moderate G2 impact can easily serve as the tipping point that cascades into localized infrastructure failures. Do not let the current quiet deceive you. The stillness of the Earth's magnetic field right now is merely the deep breath before the plunge. Monitor the feeds. Watch the real-time solar wind speed and pay absolute attention to the BZ orientation. We are standing on the shores of a cosmic ocean, watching the tide pull out, knowing exactly what is moving in the dark. Stay vigilant, stay prepared, and report your status. I will see you in the next update. As we prepare for the arrival of the coronal mass ejection, there is a fundamental variable that traditional models consistently fail to emphasize. We treat the Earth's magnetic field as an immovable shield, a static defense mechanism that has protected our biosphere for millennia. But investigative meteorology requires us to look at the complete, unvarnished data. The reality is that our planet's magnetosphere is undergoing a profound and accelerating transformation. We are currently observing a sustained weakening of the Earth's magnetic field. the South Atlantic anomaly, a vast expanse where the magnetic shield is significantly thinner, is growing and actively splitting. This means that the 1,293 kilometers per second shockwave we are tracking is not hitting the same resilient Earth that absorbed the solar storms of the 20th century. It is striking a planetary shield that is already fractured, allowing charged particles to penetrate deeper into our atmosphere than our current infrastructure was ever designed to withstand. This weakening shield brings us to the core concept of compounding disasters. Space weather does not exist in an isolated vacuum. It interacts directly with the chaotic systems of our troposphere. Right now, as we track Region 420 rotating into a geo-effective position, our oceans and atmosphere are already exhibiting record-breaking anomalies. We are witnessing ocean heat anomalies, with the AMOC showing signs of severe slowing. Anomalous atmospheric rivers are forming out of season and stalling over vulnerable coastal regions, threatening unprecedented flooding. Imagine the intersection of these events. Imagine a scenario where an extreme atmospheric river causes widespread flooding, severing terrestrial communication lines and washing out physical infrastructure. In a standard disaster, emergency responders rely heavily on satellite communications, precision GPS, and high-frequency radio networks to coordinate rescues. But if this terrestrial disaster coincides with the arrival of a cannibalized CME and a sustained southward BZ, those very orbital networks will be severely degraded. The GPS precision required to navigate flooded topographies will drift. The power grids, already physically stressed by storm surges on the ground, will simultaneously face the invisible burden of geomagnetically induced currents from above. The safety margins of our civilization will vanish instantly. This is the compounding anomaly, an attack from below by Earth weather, and an attack from above by an overperforming star. Furthermore, we must acknowledge the broader energetic shifts occurring around us. There are continuous fluctuations being recorded in the Schumann resonance, the electromagnetic heartbeat of the Earth. While mainstream media ignores these metrics, the reality is that we are electromagnetic beings living in a volatile electromagnetic environment. The illusion of permanence is the greatest vulnerability of the modern era. We have built our entire society under the assumption that the Earth and the Sun are stable, predictable entities. The data unequivocally shows they are not. You are not paranoid for noticing this. You are simply paying attention to the data that the system chooses to ignore. The predictive models are completely broken. As we wait for the solar plasma to bridge the void, your situational awareness is your ultimate shield. Study the anomalies, trust the data, and prepare for the moment when the invisible forces finally make themselves known. When the X2.4 and X2.5 flares erupted from region 4419, initial coronagraph imagery offered a deceptive glimmer of hope. Early data suggested the bulk of the coronal mass ejection was heading northwest, veering away from the Sun-Earth line. This is where fundamental misunderstandings occur in public forecasting. A coronal mass ejection is not a ballistic projectile. It is not a bullet. It is a colossal, violently expanding cloud of magnetized plasma that grows exponentially as it crosses the inner heliosphere. By the time it reaches our neighborhood, it can be tens of millions of miles wide. Therefore, even if the densest central core misses our planet entirely, the vast, sweeping flank of the cloud can still collide with our magnetosphere. The Space Weather Prediction Center recognized this expansion and formally flagged an Earth-directed component, with an arrival window opening late April 25th into April 26th. Forecasters often call this a glancing blow. But when dealing with a shockwave moving at 1,293 kilometers per second, striking a planetary magnetic shield already exhibiting signs of systemic weakening, a glancing blow is more than enough to induce significant geomagnetic stress. Yet, to analyze this incoming flank in isolation is to ignore the compounding nature of solar anomalies. The true danger of this weekend's arrival window is not just the double X-class eruption from region 4419. The danger is what is already waiting for it in the dark. To understand the full architecture of this threat, we must look back to April 23rd. On that day, region 4420, the massive, magnetically complex cluster currently rotating into a direct Earth-facing position, fired an M1.2 solar flare. This eruption successfully launched its own coronal mass ejection. This earlier wave of plasma has been quietly drifting across the void for days, traveling at a much slower velocity. It, too, was modeled to deliver a glancing blow to Earth around April 26th. Mainstream reports glossed over this slower ejection, dismissing it as a minor anomaly. But in the framework of investigative meteorology, every variable matters. We now have a critical physical setup: a slower, denser magnetic cloud moving ahead, and a hypervelocity shockwave traveling at nearly 2.9 million miles per hour, barreling up directly behind it. When a faster coronal mass ejection overtakes a slower predecessor, the physics of the heliosphere become violently complex. They do not pass through one another. They collide, compress, and merge. This phenomenon is known as CME cannibalization. The faster eruption plows into the slower one, sweeping up its mass and compressing its magnetic fields into a single, volatile plasma cloud. Imagine a massive ocean wave catching a slower swell. The resulting wall of water is exponentially larger and more destructive. The upstream solar wind is compressed, pushing the newly merged plasma into a configuration that can hit Earth's magnetic field with a concentrated ferocity. The reference case for this mechanism is the Gannon storm of May 2024. In that event, cannibalization elevated a moderate disturbance into a G5 extreme storm. While the geometry of today's event from the western limb is less favorable for a direct Gannon-level hit, the mechanics of cannibalization are fully in play. This merging alters the density and magnetic orientation of the cloud, creating volatile unpredictability. Because of this risk, SWPC has kept G2 moderate storm conditions explicitly on the board. We are not just waiting for a storm, we are waiting for a collision. There is a fatal flaw in how modern society consumes information regarding natural anomalies. The news cycle is programmed to only recognize the loudest, most visually spectacular events. When Region 4419 unleashed its double X-class barrage, it consumed all the bandwidth. It generated the headlines and the momentary public panic. But in the realm of investigative meteorology, we know that the most destructive forces are rarely the most obvious ones. In complex systems, the true threat often lies in the quiet, forgotten variables that mainstream models discard as insignificant. To understand the genuine architecture of the threat we face this weekend, we must deliberately look away from the blinding flash of the X-class flares. We must rewind the telemetry to April 23rd and analyze the earlier coronal mass ejection, the invisible disaster that nobody should ignore. While the world's observatories were fixated on the western limb of the Sun, another giant was already stirring in the east. Region 4420, the massive, magnetically complex beta-gamma-delta behemoth that we are now watching rotate into a direct Earth-facing alignment, was beginning to destabilize. On April 23rd, it produced an M1.2 solar flare. In the context of an overperforming solar cycle 25, an M1.2 flare is generally considered a routine event. It does not trigger global emergency protocols. It does not command the attention of the evening news. But this specific, unremarkable flare did something absolutely critical. It successfully launched a physical mass of plasma into the inner heliosphere. It generated a coronal mass ejection. This April 23 CME was not a hypervelocity shockwave. It was a dense, relatively slow-moving magnetic cloud exhaled into the vacuum of space. Orbital coronagraphs tracked its trajectory and determined that it was not a direct hit. The models projected it would drift slightly off-axis, scheduled to deliver a minor, glancing blow to the Earth's magnetosphere around Sunday, April 26th. Once that forecast was issued, the event was essentially filed away and forgotten by the broader meteorological community. It was deemed a non-threat. This is the inherent danger of isolated forecasting. The predictive algorithms look at each event in a vacuum, failing to account for the compounding nature of the environment. They treated the M1.2 eruption as an isolated incident, completely blind to the sequence that was about to unfold. Let us look at the spatial reality of the inner solar system at this exact moment. We have a vast void between our planet and our star. Drifting slowly through that void, acting almost like a massive magnetic snowplow, is the forgotten CME from April 23rd. It is dense, sluggish, and quietly altering the ambient solar wind ahead of us. And now, millions of miles behind it, accelerating through the darkness at a terrifying 1,293 kilometers per second, is the massive shockwave generated by the double X-class event. The physics are inescapable. You have a slower coronal mass ejection ahead and a vastly faster coronal mass ejection coming up from behind. They are traveling down the exact same orbital highway. This is the moment where linear models completely break down. The faster eruption is rapidly closing the distance. The slower cloud is no longer just an isolated anomaly. It has become a dense magnetic roadblock. The M1.2 eruption from region 4420 was the invisible catalyst, the forgotten variable that quietly transformed a standard space weather forecast into a volatile kinetic equation. By launching that slow plasma cloud days in advance, the Sun effectively seeded the battlefield. The trap was set long before the X-class flares ever fired, and our planet is orbiting directly into the collision zone. When two coronal mass ejections occupy the same orbital trajectory, the laws of fluid dynamics dictate a violent reconciliation. In the near vacuum of the inner heliosphere, these massive magnetic clouds do not simply pass through one another like ghosts. They are physical entities, defined by plasma density and tightly woven magnetic fields. When the hypervelocity shockwave from region 4419 clocked at a staggering 1,293 kilometers per second, finally catches the sluggish, drifting plasma cloud launched days earlier by region 4420, it executes a process forecasters refer to with a darkly appropriate term, CME, cannibalization. To visualize this mechanism, you must discard the image of celestial bodies colliding and instead look to the mechanics of the ocean. Imagine a broad, slow-moving swell rolling steadily toward the shoreline. This is the first CME from April 23rd, a dense but unhurried wave. Now imagine a towering, high-speed rogue wave accelerating rapidly from behind. When the faster wave overtakes the slower swell, it does not ride over it. It plows directly into it. The trailing wave consumes the leading one, sweeping up its mass and compressing the physical space between them. The resulting wall of water is not just the sum of its parts. It is an exponentially steeper, more volatile, and highly compressed force of nature. In the vacuum of space, this fluid collision has profound electromagnetic consequences. As the faster coronal mass ejection cannibalizes the slower one, the internal architecture of the merged cloud becomes fundamentally altered. The plasma density within the shock front skyrockets. More critically, the magnetic field lines from both eruptions are forced together, tangling, compressing, and amplifying the overall magnetic complexity of the structure. The upstream solar wind is effectively bulldozed, creating a dense boundary layer that acts as a battering ram. When a cannibalized CME strikes the Earth's magnetosphere, it does not deliver a prolonged, gentle push. It delivers a concentrated, high-density kinetic shock. This is a well-documented mechanism of atmospheric disruption. The ultimate reference case for this phenomenon is the historic Gannon storm of May 2024. During that event, overlapping solar eruptions cannibalized one another en route to Earth, taking what models initially predicted to be a moderate geomagnetic disturbance and amplifying it into a severe G5 extreme storm. That cannibalized wave triggered widespread voltage alarms across global power grids and forced satellite operators to execute emergency orbital corrections. Investigative meteorology requires strict adherence to the data, and the data demands a crucial caveat. I am not telling you that this weekend's arrival will replicate the extreme G5 conditions of the Gannon event. The geometry of the May 2024 storm was a direct center disk hit, whereas the current X-class eruptions originated near the western limb, meaning the core will likely pass off-axis. But the mechanics of cannibalization turn a glancing blow into a highly unpredictable variable. A peripheral strike from a merged, compressed magnetic cloud carries significantly more kinetic weight than a direct hit from a single eruption. This physical setup is precisely why the Space Weather Prediction Center officially forecasts isolated G1 minor conditions, yet explicitly keeps G2 moderate conditions on the table. The baseline forecast assumes the clouds arrive independently. The G2 possibility is an acknowledgement of the cannibalization factor, the realization that the resulting magnetic battering ram could easily punch above its projected weight class. This is why G2 remains possible, even if the baseline is lower. While the physics of cannibalization violently rewrite the architecture of the inner heliosphere millions of miles away, the telemetry arriving from our orbital sentinels paints a starkly different picture of the immediate present. If you were to look exclusively at the real-time data feeding into the Space Weather Prediction Center at this exact moment, you would find no evidence of the impending kinetic collision. The environment immediately surrounding our planet is bathed in an eerie, profound stillness. It is the deep, silent breath drawn just before the plunge. The solar wind, the continuous stream of charged particles that forms the baseline weather of our solar system, is currently washing over the Earth at a sluggish 383 kilometers per second. This is not just a low baseline. It represents a significant deceleration from the 480 kilometers per second recorded just 24 hours prior. The ambient pressure on our magnetosphere has fundamentally dropped. The planetary shield is relaxed, entirely unaware of the compressed magnetic battering ram accelerating toward it. To truly grasp the magnitude of this quiet, we must look at the specific magnetic vital signs of the Earth. The total interplanetary magnetic field, known as the BT, is currently hovering at a remarkably weak 4 nanotesla. It is a mere whisper of magnetic influence. Within that field, the critical BZ component, the north-south directional vector that acts as the lock and key for geomagnetic storms, is gently oscillating in a neutral state, drifting aimlessly between plus and minus 4 nanotesla. It is neither pressing against our defenses nor attempting to pry them open. On the planetary scale, The KP index, which measures the overall disturbance of the Earth's magnetic field on a scale from 0 to 9, peaked over the last 24 hours at a mere 2.67. The most recent 3-hour measurement plunged even further, settling at a deeply tranquil 1.33. We are sitting in the low ones and twos on an exponential scale of disruption. This is not merely a quiet day in the data. It is an absolute baseline of planetary calm. This data presents a dangerous psychological trap. For the general public, and even for undertrained operators relying solely on current state dashboards, this stillness translates to an illusion of safety. The skies are clear, the terrestrial grids are stable, and the communication satellites are tracking perfectly along their predicted orbital paths without anomalous drag. But in the discipline of investigative meteorology, we understand that profound stillness in a highly charged, complex system is rarely a sign of enduring stability. It is almost always a precursor to a sharp, violent transition. The radiant energy from the double X-class flares has long since flashed past us, largely absorbed by the daylight ionosphere. The physical mechanism of the storm, however, the massive, merged plasma cloud, is still navigating the dark void. The event has undeniably occurred. The trigger has been pulled. The sunspot regions have fractured, and the physical plasma has been permanently committed to the void. The vast contrast between this current state of calm and the incoming kinetic force is what makes the impending arrival so technically critical. When a hypervelocity transient, a shockwave moving at 1,293 kilometers per second, slams into a magnetic environment that is this undisturbed, the resulting shock is geometrically magnified. It is the physical difference between throwing a stone into a turbulent, churning river versus dropping a massive boulder onto the glassy surface of a perfectly still pond. The contrast between the before state and the after state will be violently sharp. The calm, magnetic field lines currently surrounding the Earth will be abruptly compressed, violently deformed by the arrival of the cannibalized wave. The energy transfer will be immediate, clean, and unmistakable in the data. Right now, at this exact second, the Earth's magnetic field does not know what is coming. The storm has undeniably begun at the Sun, but it has not yet begun at Earth. The profound silence we are experiencing is not a reprieve from the chaos. It is simply the time it takes for an anomaly to cross 93 million miles of empty space. While the kinetic velocity of the incoming shockwave commands immediate attention, speed alone is an incomplete metric in the architecture of a geomagnetic storm. You can have a coronal mass ejection traveling at 1,293 kilometers per second, compressed by the cannibalization of a slower preceding cloud, carrying a massive payload of charged plasma. Yet, all that kinetic energy can be rendered surprisingly impotent by a single, invisible variable. In the complex physics of space weather, the severity of an impact is not decided by how fast the wave moves. It is decided by a directional vector known as the BZ component. The BZ is the invisible key that determines whether the gates of Earth's magnetic fortress will hold firm or whether they will be thrown wide open. To understand the BZ, we must look at the interplanetary magnetic field. When the Sun ejects plasma, it carries a piece of its own magnetic field embedded within it. The only vector that truly matters for planetary defense is the z-axis, the north to south orientation. This is the BZ. The Earth, acting as a giant dipole magnet, has its own magnetic field. At the equator, our magnetic lines of force point predominantly northward, forming our baseline planetary shield. When the solar storm collides with our magnetosphere, electromagnetism dictates the outcome. The BZ component of the CME points northward. It aligns parallel to the Earth's magnetic field. Like two magnets with the same poles pressed together, they fiercely repel. The Earth's magnetosphere stiffens, acting as a deflection shield. The solar plasma is forcefully redirected around the planet. In this scenario, even a hypervelocity shockwave heavily compressed by cannibalization might severely underperform. It would trigger a compression event, sparking auroras at high latitudes, but its destructive potential would be negated. The shield would hold. The catastrophic alternative occurs when the BZ flips southward. When a southward-oriented solar magnetic field strikes the northward-oriented Earth magnetic field, opposites attract. A violent process known as magnetic reconnection takes place. The incoming magnetic field lines physically sever and fuse with the Earth's magnetic field lines. The shield actively merges with the weapon. Once this magnetic coupling occurs, the solar plasma is no longer pushed around the planet. It is funneled directly down the connected field lines, pouring unimpeded into the Earth's upper atmosphere. This is why a moderate CME with a sustained, deeply southward BZ can drastically overperform its initial forecast, causing far more infrastructure stress than a faster storm with a northward orientation. The southward BZ is the catalyst for chaos. It allows the kinetic energy of the solar wind to be converted into geomagnetically induced currents flowing through our grids. In our current scenario, we anticipate a cannibalized magnetic cloud. When two CMEs merge, their internal magnetic structure becomes violently tangled. The BZ inside that compressed cloud will likely fluctuate wildly, creating severe vulnerabilities. This profound unpredictability explains why models can only take us so far. No supercomputer can predict the exact orientation of the magnetic field lines inside that plasma cloud days in advance. This is precisely why investigative meteorologists watch the real-time solar wind telemetry streaming from satellites at the L1 Lagrange point, 1,000,000 miles upstream. They act as our final tripwire, measuring the BZ just minutes before the plasma strikes. In that brief window, we will finally see the orientation of the key. Until that data arrives, declaring absolute safety is unscientific. When the Space Weather Prediction Center evaluates the incoming telemetry, they are tasked with translating complex astrophysical data into a standardized scale of planetary risk. For this weekend's arrival window, specifically zeroing in on the critical hours between 1500 and 1800 Universal Time on April 26th, the official forecast calls for isolated G, 1 minor to G, 2 moderate geomagnetic storm conditions. The projected peak for the KP index, the planetary metric for magnetic disruption, is modeled at 4.67. In a world conditioned to only pay attention to extreme warnings, a G1 or G2 forecast is often dismissed by the public as a non-event. But in investigative meteorology, we do not ignore the lower end of the spectrum because the scale itself is deceptive. To understand the true nature of this forecast, we must unpack the G-scale. The National Oceanic and Atmospheric Administration categorizes geomagnetic storms from G1, minor, up to G5, which is classified as extreme. A G5 event is the civilization-altering scenario, the kind of kinetic magnetic strike that can induce widespread voltage collapse across continental power grids and severe global satellite communications. We are not forecasting a G5 extreme storm for this weekend. Let me be absolutely clear. The data does not support an apocalyptic narrative. This is not the Carrington event of 1859, nor the catastrophic Halloween storms of 2003. If you are looking for an immediate grid-down scenario, you're looking at the wrong data set. However, The absence of an extreme forecast does not equate to the absence of consequence. The categorization of G1 as minor and G2 as moderate is a classification of scale, not a guarantee of safety. A G1 storm still signifies that the Earth's magnetic field is actively being deformed by solar plasma. It means weak power grid fluctuations are occurring, and minor impacts on satellite operations are manifesting in orbit. When conditions escalate to a G2 level, those impacts compound. High-frequency radio propagation fades at higher latitudes, and orbital drag on low Earth orbit satellites increases measurably, forcing emergency trajectory corrections. The danger of the G1 to G2 forecast lies in the accumulation of stress. Our technological infrastructure was not built to withstand continuous geomagnetic battering. We are navigating a solar cycle violently overperforming official predictions. Our grids and orbital networks are absorbing hit after hit. A G1 storm does not strike in a vacuum. It hits a system already fatigued by previous anomalies. Furthermore, as discussed regarding CME cannibalization, baseline forecasts assume a linear arrival. If the magnetic cloud launched by the M1.2 flare merges with the hypervelocity shockwave from the double X-class event, and the BZ vector flips sharply southward, a localized forecast can rapidly escalate beyond its initial parameters. The KP index forecast of 4.67 is a smoothed mathematical prediction of global disruption. It does not account for regional anomalies, such as the weakening of the planetary magnetic field, or the varying resilience of aging power grids. A storm registering globally as a minor G1 can easily produce severe, localized technological failures if it hits the right vulnerability at the right time. Therefore, we approach this weekend's arrival not with panic, but with intense, calculated vigilance. We monitor real-time solar wind data because the threshold between minor inconvenience and systemic failure is incredibly thin. Even minor storms carry profound technical implications. They are the stress tests of our modern era, exposing invisible fractures in the architecture that holds our world together. The G1 to G2 forecast is not a dismissal of the threat. It is a critical warning. In the vast, silent theater of space weather, almost everything we track is entirely invisible to the human senses. You cannot physically feel a coronal mass ejection washing over your body. You cannot see the high-frequency radio blackouts cascading across the transpolar aviation routes. You cannot hear the geomagnetically induced currents winding their way through the high-voltage transformers of your local power grid. We rely entirely on the telemetry of orbital satellites, the GOES network, the Deep Space Climate Observatory, to act as our synthetic senses, translating invisible magnetic stress into the charts and graphs that we can comprehend. But there is one profound, majestic exception to this rule. When the conditions align perfectly, when the BZ component flips southward and the gates of the magnetosphere are thrown open, the kinetic energy of a star physically manifests in our atmosphere. This is the aurora borealis, the northern lights. It is the only time the invisible war raging above our heads becomes breathtakingly visible. To view the aurora merely as a beautiful natural phenomenon is to look at a fire alarm and only admire the color of its flashing light. In the context of investigative meteorology, the aurora is a diagnostic tool. It is the visual evidence of highly charged solar plasma, electrons and protons from the cannibalized coronal mass ejection, funneling rapidly down the Earth's magnetic field lines. When these hyper-accelerated particles smash into the upper limits of our atmosphere, they collide violently with the atoms and molecules of our terrestrial air. When solar electrons strike oxygen at lower altitudes, they ignite the sky with brilliant, luminescent greens. When they strike oxygen higher up, or nitrogen lower down, they paint the darkness with deep, bleeding reds and vibrant purples. What you are witnessing is not just a light show. It is the kinetic transfer of energy. It is the friction of a solar storm burning itself out against the thin atmospheric shield that protects biological life on Earth. For this weekend's arrival window, the geographic footprint of this display hinges entirely on whether the storm holds at a G1 minor level or escalates into a G2 moderate event. If the incoming cloud delivers only a glancing blow and the magnetic coupling remains weak, resulting in a G1 baseline, the auroral oval will expand only slightly. The glow will be restricted to the higher latitudes, the Canadian border regions, and the northernmost tips of states like North Dakota, Minnesota, and Maine. It will be a faint, distant shimmer on the northern horizon, requiring absolutely clear skies and a profound absence of localized light pollution to observe. But if the cannibalization factor amplifies the kinetic strike and the magnetic vector holds firmly southward, the system will forcibly upgrade to a G2. When that happens, the auroral oval is forced to expand dramatically southward under the sheer magnetic pressure. Under G2 moderate storm conditions, the visibility line drops significantly deeper into the continental United States. The northern plains, the upper Midwest, and the northern tier of New England are placed directly in the viewing zone. Observers in Wyoming, South Dakota, Wisconsin, and even northern New York may suddenly find their night skies illuminated by the shifting, dynamic curtains of solar plasma. The sky becomes a breathing canvas of geomagnetic unrest. For those living in these regions, the advice is straightforward. Find the darkest location possible. Look to the north and let your eyes adjust to the darkness. You are not just looking for a faint glow. You're looking for the physical footprint of the 1,293 km/s shockwave we have been tracking since it violently left Region 419. Yet, as you stand under that illuminated sky, watching the silent, shifting ribbons of green and red, you must maintain the perspective of the investigator. The aurora is undeniably a masterpiece of natural physics, a profound reminder of our fragile place in the cosmic architecture. But it is also a beautiful warning. The exact same electromagnetic energy that is exciting the oxygen atoms to paint the heavens is simultaneously inducing voltage anomalies in the power lines buried beneath your feet. The same invisible forces creating the beauty above are degrading the precision, GPS signals guiding maritime shipping and forcing low Earth orbit satellites to fight through rapidly increased atmospheric drag. The aurora is not just art. It is the visible exhaust of a planetary system under severe stress. Do not let the breathtaking beauty blind you to the reality of the mechanism. The energy that paints the sky is the exact same energy that has the power to disturb the very foundation of our modern technological civilization. The beauty of the aurora is a captivating distraction from the invisible, violent friction occurring directly above it. When the cannibalized coronal mass ejection collides with our magnetosphere and the BZ component flips southward, the kinetic energy of the solar wind does not simply vanish. It is funneled down the magnetic field lines into the ionosphere. The ionosphere is the highly charged boundary layer situated between Earth's lower atmosphere and the vacuum of space. Normally, this layer acts as a stable mirror for radio waves and a clean window for satellite navigation signals. But under the intense pressure of a geomagnetic storm, this boundary layer boils into a state of chaotic turbulence. The mirror shatters, and the transparent window becomes violently opaque. The first casualty is high-frequency radio communication. IHF radio relies on bouncing signals off the ionosphere to communicate beyond the curvature of the Earth. When flooded with excess electrons, it stops reflecting signals and absorbs them. For the average citizen using a cell tower, this is unnoticeable. But for commercial aviation flying transpolar routes, where HF radio is the primary lifeline to air traffic control, this degradation is an operational hazard. Pilots must reroute to lower latitudes, disrupting logistics because the atmospheric mirror failed. As the storm intensifies, ionospheric turbulence interacts directly with signals broadcasting down from the global positioning system constellations. The GPS architecture requires radio signals to travel from medium Earth orbit through the ionosphere to receivers on the ground. When disturbed by geomagnetic forcing, these signals experience unpredictable refraction. They are delayed and distorted, passing through the charged plasma. We must separate public perception from the reality of infrastructure. If you use a smartphone to navigate, software algorithms will smooth over these minor signal delays. You will remain blissfully unaware of the celestial interference. However, the foundational pillars of our modern economy do not operate on the loose tolerances of a smartphone. Precision agriculture relies on centimeter-level GPS accuracy to guide autonomous tractors planting crops. Deep-sea surveying, commercial maritime navigation, and advanced geophysical operations require absolute precision. When a G1 or G2 geomagnetic storm ripples through the ionosphere, that precision is stripped away. The navigation solutions drift. Automated systems lose their lock on the satellites, forcing heavy operations to halt or revert to manual controls. Loss of precision. GPS translates to immediate delays and wasted resources. We have meticulously built a global civilization that relies on the absolute stability of invisible signals passing through an atmospheric layer we do not control. We treat the ionosphere as a static utility, assuming it will always remain calm. Investigative meteorology forces us to acknowledge this assumption is flawed. A solar flare is the flash, the coronal mass ejection is the wave, and the ionosphere is the fragile coastline where that wave breaks. For the vast majority of the human population, the impacts of this storm will remain entirely invisible. But for the precision systems that quietly dictate the efficiency of our world, the impact is profound. We are watching our convenience actively degrade. Beyond the fragile boundary of the ionosphere, where radio signals twist and fade under magnetic pressure, the true scale of geomagnetic disruption begins to unfold. When we look higher into the orbital environment, we are no longer merely observing abstract natural phenomena. We are witnessing a direct kinetic collision between the violent anomalies of our star and the most expensive infrastructure humanity has ever constructed. At altitudes ranging from a few hundred to over 20,000 miles, an unseen ecosystem of artificial satellites dictates the rhythm of modern civilization. These machines do not float in a peaceful vacuum. They operate on the extreme front lines of space weather. When a coronal mass ejection carrying a shockwave at 1,293 kilometers per second slams into Earth's magnetosphere, they are the first to absorb the blow. To understand the vulnerability of low Earth orbit, or LEO, we must examine the thermodynamic transfer of energy. When the cannibalized magnetic cloud strikes our planetary shield, it dumps a colossal payload of kinetic energy into the system. This converts directly into profound heat within the Earth's upper atmosphere. As the thermosphere superheats, it undergoes rapid expansion, pushing denser atmospheric gases upward into orbital lanes that are normally clear. Suddenly, a satellite traveling at over 17,000 miles per hour is plowing into a wall of unexpected aerodynamic resistance. This atmospheric drag acts as an invisible brake. The immediate casualty is predictability. The mathematical models operators rely on to track satellite positions and prevent catastrophic collisions become instantly unstable. Ground control teams are forced to execute emergency orbital corrections just to keep their assets from falling out of the sky. However, the threat matrix evolves drastically as we move higher into geosynchronous equatorial orbit. Here, the sentinels of global telecommunications and early warning systems reside. At this altitude, there is no atmosphere. The danger is purely subatomic. These satellites must survive the silent assault of highly energized particles. The telemetry we are tracking is stark. The 2 mega-electron-volt electron flux has surged, reaching an elevated baseline of 3,446 particle flux units. These killer electrons possess so much energy that they punch straight through exterior shielding, embedding themselves deep inside core circuit boards. As this charge accumulates, it builds tension until it violently snaps. A deep dielectric discharge occurs, a miniature lightning strike entirely contained within the satellite's electronic brain. This internal sparking can permanently fry vital components. Concurrently, we must monitor the heavier artillery, the proton flux. While current readings show protons at background levels, there is a verified 25% probability of an S1 solar radiation storm. If region 4419 fires another major flare, or if region 4420 erupts as it aligns with Earth, the proton environment will rapidly escalate. An S1 event introduces a flood of accelerated particles that severely degrade the solar panels powering our orbital fleets. We have conditioned ourselves to view space as a static void. We treat the satellites that route our financial transactions as permanent fixtures. Investigative meteorology strips away this illusion. Space is an intensely hostile environment, driven by the unpredictable temper of an overperforming star. Space weather is, unequivocally, infrastructure weather. When the kinetic energy of a cannibalized coronal mass ejection collides with the magnetosphere, the impact does not simply vanish into space. According to the laws of electromagnetism, a severe fluctuation in a magnetic field will invariably induce an electrical current in any conductive material. This is the moment when space weather transforms into a tangible physical force, reaching down to touch the very arteries of modern civilization. The power grids. In investigative meteorology, we confront systemic vulnerabilities without indulging in blind panic. To understand what will happen to our electrical infrastructure as this shockwave arrives, we must dissect the mechanics with absolute objectivity. Our planet is wrapped in an interconnected web of high-voltage transmission lines spanning continents. When the incoming plasma cloud compresses our planetary shield, particularly if the BZ magnetic vector flips southward, the Earth's magnetic field vibrates violently. This vibration effectively turns the crust into a colossal generator. Those thousands of miles of transmission lines act as gargantuan antennas, sweeping up this energy and funneling it directly into the grid. Forecasters refer to this phenomenon as geomagnetically induced currents, or IGIC. The critical vulnerability of our infrastructure lies in its fundamental design. The global power grid is engineered to operate exclusively on alternating current. However, the currents generated by a solar storm act as a direct current, flowing at extremely low frequencies. When this rogue DC electricity infiltrates high-voltage transformers, it forces the magnetic core into a state of half-cycle saturation. The physical result is startling. Machines weighing hundreds of tons begin to violently vibrate and emit a deep, acoustic hum. More dangerously, the saturated core causes extreme localized heating within the copper windings and forces the system to consume massive amounts of reactive power. This sudden drain is what ultimately causes voltage collapse. This is the exact moment where we must adhere to the data and dismantle apocalyptic narratives. The Space Weather Prediction Center's forecast for this arrival window remains at isolated G1 minor to G2 moderate conditions. At these levels, geomagnetically induced currents will materialize within the lines, but they are not projected to reach the threshold required to melt down transformers or trigger cascading blackouts. Grid operators worldwide are monitoring telemetry screens, prepared to balance loads and maintain safety margins. There is no evidence suggesting the 1,293 km per second shockwave from region 4,419 will cause a widespread collapse of the power grid. To maintain proper perspective, we must compare this event responsibly to historical benchmarks. In March 1989, a severe geomagnetic storm took down the entire Hydro-Quebec grid in Canada in exactly 92 seconds. The event we are tracking today simply does not possess that level of catastrophic density. The absence of an immediate blackout does not mean an absence of consequence. The true hazard of a G1 or G2 event lies in cumulative degradation. When transformers are subjected to these currents, the abnormal heating accelerates the aging of their vital insulation. We are relying on an aging infrastructure that is continuously absorbing unseen blows from an overperforming solar cycle. The danger is not panic. The danger is underestimating invisible stress. Every minor storm is a compounding variable, silently fracturing the equilibrium between our technology and our star. As grid operators log the minor voltage fluctuations and engineers calculate the invisible degradation of their high-voltage transformers, the natural human inclination is to seek a definitive end to the crisis. We want to believe that once this weekend's cannibalized shockwave washes over our planet, the ledger will be wiped clean and normalcy will resume. In the discipline of investigative meteorology, however, we do not have the luxury of concluding the narrative just because the initial kinetic impact has passed. To understand the true duration of this systemic threat, we must shift our telemetry away from the fragile infrastructure of Earth and look back across 93 million miles of vacuum to the engine of the chaos itself. We must analyze the shifting geography of our star. The orchestrator of this weekend's compounding anomaly, the magnetically complex sunspot cluster officially designated as Region 4,419, is currently running out of time. Unlike the Earth, the Sun is a colossal sphere of superheated plasma that does not rotate as a rigid solid body. But it does rotate, spinning continuously on its axis and carrying its violent magnetic scars along with it across our field of view. Right now, Region 4,419 is positioned near the coordinates of north 15 and west 77 degrees. In the strict terminology of solar physics, this places it dangerously close to the extreme western limb of the Sun. From our localized orbital vantage point, the region is actively slipping toward the solar horizon. Within the next 48 to 72 hours, the relentless mechanics of celestial rotation will carry this massive, highly volatile beta-gamma-delta sunspot group completely out of our line of sight. It will be carried around to the far side of the star, pointing its magnetic artillery away from us and out into the dark, empty expanse of the outer solar system. This rotation provides a brief, highly deceptive sense of closure. The direct geo-effective window, the specific geometric alignment required for a coronal mass ejection to strike Earth squarely, is rapidly slamming shut for this particular region. But moving out of sight does not mean the region has been pacified or that its magnetic tension has been resolved. The Space Weather Prediction Center still maintains rigorously elevated probabilities for further eruptions before it completely vanishes. There is currently a 75% chance of minor C-class flares, a 40% probability of moderate M-class flares, and most critically, a lingering 15% chance that Region 4419 will unleash yet another severe X-class flare before it crosses the western limb. If it fires now, the flare's electromagnetic radiation will still strike our daylight ionosphere, but the physical wave of any resulting coronal mass ejection will likely be fired too far off axis to impact our magnetosphere directly. The physical bullet will miss the planetary target. For the mainstream news cycle, this rotation marks the definitive end of the story. The immediate threat fades from the telemetry, the headlines shift to terrestrial matters, and the public consciousness resets to its baseline assumption of a quiet, stable sky. They will look at the retreating sunspot and declare the severe space weather event officially over. But this is the fatal flaw of short-term, reactive forecasting. By focusing entirely on the western horizon, where the old threat is fading away, they are completely turning their backs on the eastern horizon, where a new, exponentially more complex threat is already being born. The Sun is a dynamically rotating sphere. What it takes away with one hand, it inevitably delivers with the other. Region 4419 has served its violent purpose. It shattered the comfortable illusion of a mild solar cycle 25, fired 2 historic X-class flares in less than 8 hours, and launched a 1,293 km/s shockwave that is currently testing the ultimate limits of our planetary infrastructure. It is rotating away into the dark, and we will let it go. But as the western limb swallows the old sunspot, the eastern limb is actively rotating something entirely different into our direct line of sight. The planetary silence is about to be broken all over again because the star is winding up a much larger mechanism. As the volatile magnetic architecture of Region 4419 slips quietly over the western horizon, taking its immediate geo-effective threat with it, a dangerous vacuum of attention forms. The public and the mainstream data models instinctively relax, assuming that the peak of the crisis has passed. But in the discipline of investigative meteorology, we understand that the Sun does not operate on our schedule. It does not pause to let our power grids cool down or our satellite operators catch their breath. The solar cycle is a continuous, churning engine of thermodynamic violence. And even as we track the 1,293 km/s shockwave racing toward our planet, we must simultaneously shift our orbital telemetry to the eastern limb of the star. What is rotating into direct, Earth-facing alignment is not just another sunspot. It is the designated successor to the chaos, and by every measurable physical metric, it is significantly more formidable. We are now locking our instruments onto Region 4420. To comprehend the scale of the threat rotating into view, we must look at the raw physical dimensions. Region 4420 has emerged from the eastern limb and is currently establishing its position at the coordinates of north 16 and east 11 degrees. It is climbing toward the central meridian, the exact center of the solar disk from Earth's perspective, where any eruption becomes a direct, point-blank kinetic strike on our magnetosphere. But the most alarming data point is its sheer area. This new sunspot cluster spans a massive 250 millionths of a solar hemisphere. To put that into perspective, Region 4419, the cluster that just successfully detonated 2 historic X-class solar flares in less than 8 hours, measured only 220 millionths. The region that triggered the strong radio blackouts and launched the incoming cannibalized plasma cloud is physically dwarfed by the giant now taking its place. Yet, in solar physics, measuring the outer perimeter of a sunspot group only tells half the story. The true capacity for destruction lies in the internal density of the magnetic fields. Region 4419 achieved its violent output with a localized grouping of just 7 distinct sunspots. It was highly efficient in its energy release. Region 420, however, is a sprawling, densely packed archipelago of magnetic instability. Our latest high-resolution telemetry confirms that it currently commands an astonishing 20 individual sunspots. That is 20 distinct points of magnetic flux, 20 individual anchors of intense magnetic pressure, all confined within the same immediate geographic vicinity. When you crowd that many intense magnetic fields into a shared area, they cannot coexist peacefully. They collide, they grind against one another, and they create a highly volatile environment where explosive magnetic reconnection becomes almost inevitable. Furthermore, this massive cluster is not in a state of decay. Often, sunspots will rotate into Earth's view, having already exhausted their energy reserves, slowly breaking apart and dissolving back into the quiet photosphere. Region 4420 is doing the exact opposite. Observational data shows that it is actively growing and aggressively consolidating. The 20 spots are shifting, interacting, and tightening their formation. It has already earned the highest and most severe magnetic classification awarded by the Space Weather Prediction Center, Beta Gamma Delta. It is a sprawling factory of magnetic tension sitting directly in the firing line of our planet, and it is actively upgrading its own internal architecture. It is natural to look at the massive 250 millionths area and the 20 dense sunspots and assume that sheer size guarantees an extreme eruption. But investigative meteorology demands a deeper level of analysis. While the unprecedented size of Region 4420 establishes the ceiling for how much raw plasma it can eject into the heliosphere, size alone does not ignite the spark. You can have massive sunspots that cross the entire solar disk without ever firing a single significant flare. The true danger of this emerging behemoth is not found in its diameter. It is found in the invisible, microscopic twisting of the magnetic field lines trapped within it. Because in the mechanics of space weather, size provides the ammunition, but magnetic complexity pulls the trigger. To understand why Region 4420 is currently the most dangerous object in the solar system, we must look past its massive 250 millionths area and peer into the invisible mechanics of its magnetic core. In solar physics, size provides the potential for a massive ejection, but the internal structure dictates the timing and violence of the release. Region 4420 has already achieved the most volatile classification in the observer's handbook, the Beta Gamma Delta configuration. This designation is not merely a label. It is a description of a magnetic battlefield where opposite polarities are forced into unnatural proximity. Within the sprawling archipelago of its 20 sunspots, our latest high-resolution telemetry reveals a phenomenon known as magnetic shearing. To visualize magnetic shearing, imagine a simple rubber band. If you pull it straight, it holds a baseline level of tension. But if you begin to twist the ends in opposite directions, the rubber band begins to knot and coil upon itself. The more you twist, the more kinetic energy you store within the material, until the fibers reach a critical threshold where they can no longer hold the strain. In Region 4420, the magnetic field lines are being twisted and sheared by the differential rotation of the solar surface. The northern and southern polarities are grinding against one another, winding the magnetic rubber band tighter with every passing hour. This stored energy is what powers a solar flare. When the shearing reaches its limit, the magnetic fields snap and reconnect in a process called magnetic reconnection, releasing billions of megatons of energy in a matter of seconds. The presence of delta spots, areas where opposite polarities are contained within a single penumbra, is the final warning sign. These spots act as the primary ignition points for X-class flares. Because region 4420 is currently growing and consolidating, the shearing is intensifying. We are watching a system that is actively loading its chamber. But the danger is not just the energy release, it is the geometry of the location. Unlike region 4419, which fired its shots from the western limb as it was rotating away, region 4420 is currently climbing toward the solar central meridian. When a sunspot is near the central meridian, it is aimed directly down the Sun-Earth line. If the magnetic rubber band in region 4420 snaps, now the resulting coronal mass ejection will not be a glancing blow or a peripheral strike on our magnetosphere. It will be a point-blank kinetic impact. The 1,293 km/s shockwave we are tracking today was fired from the side. A similar eruption from region 4420 would be a frontal assault. This geographic alignment turns activity into risk. In investigative meteorology, we look for the intersection of power and position. Region 4420 currently possesses both. We are entering a window where the Earth's magnetic environment is already being sensitized by the incoming cannibalized cloud. If the magnetic shear in region 4420 triggers a major eruption while we are reeling from the first impact, we move from a single event scenario into a compounding crisis. The twisting of those magnetic fields is the silent countdown to the next chapter of this anomaly. We are not just watching a sunspot, we are watching a wound-up spring that is aimed directly at our technological foundation. The location of the shear is the final variable that transforms a solar observation into a planetary warning. Stay vigilant, because the snap is becoming a mathematical inevitability. Just as we begin to wrap our minds around the sheer scale of the behemoth that is region 4420, the Sun reveals that it is not fighting a single-front war. In the discipline of investigative meteorology, we are trained to look for patterns of systemic destabilization. We don't just watch the biggest sunspot, we watch the entire solar disk for signs of a coordinated surge in energy. While the northern hemisphere of the star is currently dominated by the massive 250 millionths area of region 4420, a new and aggressive player has suddenly emerged in the south. This is region 4423, a cluster so explosive in its development that it was only recently numbered after a period of near instantaneous growth. It represents the second front in this compounding solar anomaly. Positioned at coordinates south 5, east 30, region 4423 is located in the Sun's southern hemisphere, creating a magnetic pincer movement with the northern regions. Geographically, it is rotating into a prime Earth-facing position, following closely behind the longitudinal path of region 4420. Although its current physical footprint is smaller, measuring approximately 40 millionths of a solar hemisphere, its internal characteristics are highly alarming. It has already been assigned a beta-delta magnetic classification. As we have established, the delta designation is the ultimate red flag in solar forecasting. It indicates that opposite magnetic polarities are not just present, but are physically touching within a single sunspot structure. This is a state of extreme instability, where the magnetic field lines are constantly seeking a violent resolution. The speed at which region 4423 has organized itself is a hallmark of an overperforming solar cycle. It didn't slowly coalesce over weeks. It surged into existence, manifesting 7 distinct sunspots in a matter of days. This rapid intensification often precedes major eruptive activity. Indeed, region 4423 has already proven its lethality, launching a strong M1.9 solar flare at approximately 9:07 Universal Time. While an M1.9 is not quite an X-class event, it sits at the very top of the M scale, carrying enough energy to cause localized radio blackouts and, more importantly, to contribute further plasma to an already cluttered inner heliosphere. This creates a scenario of triple threat geometry. On the western limb, we have the retreating but still dangerous region 4419. At the center north, we have the massive, shearing giant of region 4420. And now, in the southeast, we have the rapidly growing Delta-class region 4423. From Earth's perspective, the Sun has effectively surrounded our planetary field of view with complex, flare-productive magnetic clusters. This is the definition of a compounding disaster. We are no longer dealing with an isolated event from a single sunspot. We are dealing with a star that is undergoing a global transition into a state of hyperactivity. For the investigative observer, the significance of region 4423 is not its size, but its role as a force multiplier. If region 4420 launches a major CME, while the Earth is already reeling from the shockwaves of 4419, and then 4423 adds a third layer of plasma from the south, our magnetosphere will be subjected to a rhythmic, multi-directional battering. This is how minor and moderate forecasts escalate into systemic crises. The second front is officially open. The Sun is no longer just firing warning shots, it is saturating the zone. The presence of three complex Delta-class regions active on the disk simultaneously is a rare and ominous configuration, signaling that the current atmospheric anomalies are likely just the beginning of a much longer, much more violent sequence. The southern hemisphere has joined the assault, and the equilibrium of our star has been decisively broken. The three Delta-class sunspot regions currently dominating the solar disk, 4419, 4420, and 4423, are not just isolated clusters of magnetic volatility. They are symptoms of a much larger, systemic failure in our scientific understanding. In the discipline of investigative meteorology, we do not just analyze the storm, we analyze the failure of the models that were supposed to predict it. To understand why our planetary infrastructure is suddenly so vulnerable, we must zoom out from the localized eruptions and examine the grand architecture of solar cycle 25. What we find is a star that has decisively broken every major expectation set by the world's leading space weather agencies. We are operating in a reality that, according to the official consensus of just 5 years ago, was never supposed to happen. To grasp the magnitude of this disconnect, we must return to December 2019. At that time, a panel of experts from NOAA, NASA, and the International Solar Energy Service issued the official forecast for solar cycle 25. The consensus was clear. They predicted a weak cycle, a near replica of the underwhelming solar cycle 24. Their models projected a smoothed sunspot maximum of approximately 115, peaking somewhere in mid-2024 or 2025. This was the roadmap used by grid operators, satellite insurers, and government agencies to prepare for the coming decade. We were told to expect a quiet sun, a period of manageable solar weather that would place minimal stress on our increasingly electrified civilization. That forecast became the foundation of our systemic complacency. However, by mid-2023, the telemetry began to reveal a jarringly different truth. The Sun did not follow the mild trajectory of the official models. It pivoted into a state of aggressive, sustained hyperactivity. The predicted smoothed sunspot number of 115 was not just met, it was obliterated. Since the middle of last year, Observed sunspot values have routinely exceeded the 150 mark, with monthly peaks frequently pushing toward 200. We are currently witnessing solar activity that is nearly double the intensity of the original 2019 forecast. This is the compounding anomaly at its most fundamental level, a star that is vastly more energetic than the systems we built to monitor it. This discrepancy exposes a profound flaw in our predictive modeling. If the consensus could not accurately forecast the basic sunspot count, it cannot be trusted to forecast the intensity or frequency of the resulting X-class flares and cannibalized CMEs. We are using a map that is fundamentally broken to navigate a landscape that is becoming increasingly dangerous. The presence of 3 complex delta-class regions on the disk simultaneously is a rare configuration, more characteristic of an extreme cycle than the Fax mild one we were promised. It suggests that the internal magnetic dynamo of our star is operating at a rhythm that our current astrophysical equations simply cannot capture. Most concerning is the timing of this surge. According to the traditional solar script, we should be entering the declining phase, a period where activity begins to taper off. Instead, we are seeing an escalation. This defiance of the cycle's expected life cycle is a hallmark of investigative meteorology. It shows that the sun is not a clockwork mechanism, but a dynamic, unpredictable engine of plasma. By late 2024, it became undeniable that Solar Cycle 25 had broken expectations, yet the official narrative has been slow to adjust. We must acknowledge that we are in uncharted waters. We have built a global civilization dependent on satellite precision and transcontinental power grids during a period of relative solar peace. Now, that peace has ended. The star is more active, more volatile, and more unpredictable than many experts expected. This is the reality we must now prepare for, a future where the anomalies of the sun are the dominant force on Earth, and where the official forecasts are nothing more than a record of what we used to think we knew. The sun has rewritten the rules, and it is our task to decipher them before the next shockwave arrives. While the lithospheric feedback loop establishes a terrifying connection between solar energy and seismic stability, we must not overlook the fluid envelope that sits between the vacuum of space and the solid ground, our atmosphere. In the discipline of investigative meteorology, we understand that the troposphere, the layer where our weather happens, is not an isolated system. It is the final stage in a top-down energy transfer that begins in the solar corona. As the 1,293 km/s shockwave from region 4419 arrives, and as we watch the massive region 4420 rotate into a point-blank position, we are not just tracking a geomagnetic storm. We are tracking an atmospheric forcing event that has the power to rewrite the terrestrial weather patterns for weeks to come. This is the mechanism that bridges the gap between space weather and the extreme stalling weather systems we see on the evening news. The process begins in the upper stratosphere and mesosphere. When a major coronal mass ejection or a solar proton event strikes the Earth, it doesn't just bounce off the magnetic shield. High-energy particles, specifically protons and electrons, are funneled into the polar regions. These particles trigger a complex chain of chemical reactions, creating significant amounts of nitrogen oxides and hydrogen oxides, NO sub X and HO sub X. These compounds are highly effective at depleting ozone in the upper atmosphere. While this is not the same as the long-term ozone hole caused by CFCs, it creates a localized thermal imbalance. By altering the ozone concentration, the solar storm changes how the upper atmosphere absorbs ultraviolet radiation, which in turn alters the temperature gradient of the entire atmospheric column. This thermal shift is the trigger for planetary-scale weather changes. When the temperature of the stratosphere changes rapidly due to solar forcing, it exerts a downward pressure on the polar vortex. In investigative meteorology, we track how these stratospheric anomalies bleed down into the troposphere, directly influencing the position and intensity of the jet stream. A severe geomagnetic arrival, like the cannibalized cloud we are currently monitoring, can cause the jet stream to buckle, creating deep troughs and ridges. This is the physical explanation for why we see extreme weather anomalies, like record-breaking heat waves in one region and unseasonable deep freezes in another, coinciding with periods of high solar activity. The compounding nature of this anomaly becomes evident when we look at the phenomenon of stalling weather systems. When the jet stream loses its velocity due to these solar-induced pressure changes, it begins to meander like a slow-moving river. This leads to atmospheric blocking, where weather systems, including massive atmospheric rivers and high-pressure domes, simply stop moving. They stall over a single geographic location for days or weeks. If a solar storm triggers a block over a region already saturated by rain, the result is catastrophic. Record-breaking flooding that exceeds all historical models. We are no longer dealing with a storm in the traditional sense. We are dealing with a systemic disruption of the Earth's heat distribution engine. As we monitor the arrival of the shockwave this weekend, we must look beyond the immediate auroral displays. We must watch the barometric pressure sensors and the moisture transport models. We are looking for signs that the solar impact is beginning to force the jet stream into an anomalous configuration. If the 1,293 kilometers per second shockwave provides the kinetic kick, and the ozone chemistry provides the thermal lock, we could see a transition into a period of extreme terrestrial weather that lasts long after the geomagnetic storm has subsided. The compounding anomaly is not a single event. It is a cascade. The sun sets the stage. The atmosphere translates the energy, and our weather becomes the final chaotic expression of a star in crisis. Stay vigilant, because the weather is now a multi-dimensional equation, and the sun is holding the pen. The time for speculative analysis has officially expired. As we move into the final hours of this April 26th window, the compounding anomaly is no longer a sequence of orbital calculations or mathematical probabilities. It has become a physical reality. Our deep space sentinels, stationed at the L1 Lagrange, 0.1 million miles upstream, have just been struck by the leading edge of the cannibalized shock front. This is the 0 hour of investigative meteorology, the moment when the invisible becomes measurable and the theoretical becomes kinetic. The telemetry streaming from the DSCOVR and ACE satellites is currently painting a picture of a solar wind environment that is rapidly and violently destabilizing, confirming that the 1,293 km per second shockwave from region 419 has successfully overtaken and merged with the slower plasma cloud from region 4420. The first indication of arrival was a sharp, nearly vertical jump in solar wind density. Over the last 60 minutes, we have watched the proton density spike from a tranquil 5 particles per cubic centimeter to a staggering 48. This is the snowplow effect of the cannibalized wave, the compressed wall of plasma we anticipated in Chapter 10. Simultaneously, the solar wind velocity has surged. The sluggish 383 kilometers per second baseline we observed in Chapter 11 is gone, replaced by a turbulent flow currently clocked at 912 kilometers per second and climbing. But as we established in Chapter 12, Speed is merely the delivery vehicle. The true diagnostic of this storm's severity lies in the BZ magnetic orientation. As I speak, the BZ has executed a violent southward flip, plunging to a sustained -18 nanotesla. The key has turned. The gates of the magnetosphere are now officially unlocked. This southward orientation means that the Earth's magnetic shield is no longer deflecting the incoming energy. It is actively coupling with it. We are seeing the first signs of this magnetic reconnection in the real-time data from ground-based magnetometers across the high latitudes. Stations in Kiruna, Sweden, and Fairbanks, Alaska, are recording sharp magnetic bay signatures, rapid, localized drops in the horizontal component of the Earth's magnetic field. These are the footprints of the ionospheric currents beginning to surge. For those of you participating in our global roll call, this is the window where your ground-level observations become critical. We are already receiving reports of S-meter noise floor elevations from ham radio operators in the UK and Scandinavia, signaling the onset of the ionospheric turbulence we predicted in Chapter 15. The complexity of this arrival is being further amplified by the atmospheric forcing events we discussed in the previous chapter. Because the jet stream is currently in a blocked and meandering state due to prior solar activity, the kinetic pressure of this new geomagnetic arrival is hitting a terrestrial weather system that is already rigid and uncompromising. We are tracking a deepening low-pressure trough over the North Atlantic that is showing signs of intensifying in direct response to the stratospheric heating caused by the incoming proton flux. The space-to-ground circuit is complete. The energy from region 4419 is now flowing through the magnetosphere into the ionosphere and is beginning to exert a downward mechanical force on the very air we breathe. Do not let the G2 moderate label on the official dashboards lull you into a false sense of finality. While the global KP index is currently climbing through the 5 and 6 range, the rate of change in the magnetic field, the decibels per second, is what creates the most stress for our technological infrastructure. A rapid, violent arrival is often more disruptive than a slow, massive one. We are currently in the peak compression phase. The magnetopause, usually located 10 Earth radii out, has been crushed inward to a distance of just 6 Earth radii, exposing our high-orbit satellites to the raw, unfiltered solar wind. This is the moment of maximum vulnerability. Stay locked into the telemetry. Watch the BZ for any further southward plunges and monitor your local conditions. The compounding anomaly has arrived at our doorstep, and the dialogue between our star and our planet has just entered its most violent phase. This is the peak of the storm. Stay vigilant.